All right, so what we're going to look at today are different types of data. And this is data you're going to collect maybe from surveys. It could be data made from measurements. Depending on the type of data you have, you're going to do certain kind of measurement or certain types of calculations. And some calculations you won't be able to do on certain kinds of data. So let's take a look. Now, first off, we're going to talk about the difference between parameters and statistics. In the world of statistical studies, ultimately what we wish we had were parameters. Now, what a parameter is, it's some numerical measurement for an entire population. So if we want to talk about like average height, and we're thinking about the average height of just people in general, people on planet Earth or in the space station as well, we would want to know about the average height of if you took every human being, got their height, averaged them, we would have the average height of every human being that's alive right now. So we could have like all these, like say we have Apple Watches that somehow are able to measure our height. Or maybe let's make this a little more sensible, I guess, given current technology. Let's say pulse rate. We all have Apple Watches that could measure pulse rate. Let's say every human being has one of these on the planet or in the space station, or we all have one. And all these Apple Watches record our pulse rate at a given moment and then sends the data to a supercomputer, and that supercomputer computes the average pulse rate. That would be a parameter. It is a numerical measurement, calculation using data from every single person, every single member of the population. Now, barring something like universal distribution and use of Apple Watches, we're not going to have this kind of information. So what we settle for is, instead of a parameter about our population, we settle for a statistic about our population. Now, this is an approximation of sorts. And I want to just emphasize that when we're talking about a statistic relative to a population, we're still not testing everybody in the population. We're going to test a sample. So a statistic. So, for example, well, let me just go over this. It's a numerical measurement for a sample of the population. Now, the idea is that we're going to get a sample, a smaller collection of people. Not every single human being alive today would be contributing to this. We're just going to come up with a random sample, ideally. And hopefully it's a sample that seems to represent the population, the human population, as it is right now. For example, you would have so many % of the folks in this sample would be, well, babies or infants. Certain % would be, well, people who are 60 to 70 years old. There's different kinds of things you would want to make sure that the sample has, certain traits that represent the population as a whole. And then using this sample, let's say we had 10,000 people. We would then use this sample, give everybody a free Apple Watch, and this would record an average pulse. The Apple Watches would send the 10,000 recordings at a given second to a supercomputer, maybe not even a supercomputer, just maybe a regular computer. And then it could calculate the average of the pulses. And that would give you an average pulse of the sample. And in theory, ideally, if the sample represents the population, it reflects the same characteristics of the population, the same traits, well, then this average pulse could be a good approximation for the average pulse of the entire human race. In other words, this statistic would be a good stand-in for that unknown parameter. So that's the idea of statistics and parameters. All right. So those are well, two kinds of, well, essentially study targets we're going to pursue. We wish we had a parameter, but we're going to come up with a sample and use that sample to come up with a statistic that's, well, close enough to the parameter, hopefully the parameter value for our population. Now, data that we collect, let's say we do have a sample. Now, there's different kinds of data we get from the sample. First off, quantitative. And this is numerical data. So you could think of quantitative, quantity, how much of something, what number described how much. It could be, say, how many pounds, how many ounces, what's the temperature, how many inches, how many miles, how much of something. So numerical data. The other kind of data you might collect is categorical. And key here, this is non-numeric. So categorical data could be data that's like, well, say that you're looking at the colors of cars. You might ask a question, well, is your car red or is your car blue? And so you write that down. Let's say you're doing a survey. You're trying to figure out something about the popularity of different paint jobs on cars. And so you would ask these kinds of questions. Now, you got to be careful with categorical data. Sometimes it's coded with numbers. Sometimes it's going to be coded with numbers. For example, let's say you're doing a drug study, you're testing some new treatment. And for various reasons, you want to code patients' names. There's something called a, well, there's reasons for doing this. It's a way of sort of, well, keeping bias out of a study. So we might say this: Sally is patient, I'll abbreviate patient, PAT, patient number 1. And then I might say Bob is patient number 2, and so on. And again, there's reasons for this. Now, even calling someone number 1 and number 2 could bring in a kind of bias. As we saw in the last lecture, the example where you might say, which do you like better, Ford or Toyota? And then if you ask the question differently, which do you like better, Toyota or Ford? you might get different answers depending on which brand you mention first. So we might give Sally and Bob some random number like 567,892, and this could be 567,834 or something like that. We'll give some combination of numbers, maybe really long, but something that does uniquely identify them. But you know, this might even make some kind of a bias. You have to be careful of that. But the point is that these numbers, if you tried to take, say, averages of their identification numbers, it doesn't mean anything. Usually it doesn't. So even though you might have numbers here, it's really still categorical data. An average of these ID numbers could mean nothing. Anyway. So just to mention that, category codes, even numeric ones, may have no computational value. So something to keep in mind. An example they actually use in the text that's pretty good is Social Security numbers. Sometimes Social Security numbers may be recorded. There's probably very little value in computing the average or the average of a Social Security number, a set of Social Security numbers. So just an example the textbook uses. All right. So one other thing about quantitative data. For quantitative data, you want to keep units attached, and especially if you were doing some measurements, say something like this. Let's say someone's measuring the lengths of rope for whatever reasons. They might record the lengths as 11 inches, 4 inches, 1 foot, 2 inches, 1 inch, and 1 foot. And if I don't put the inch and the foot here, well, we might be left guessing. Are we talking inches or are we talking feet? So better make sure I include my inches and include my feet here. And if you don't put any measurements on, well, or any units rather, well then we're not quite sure how you measured this. We might not be. For example, let's say you ask someone to measure temperatures. And so I put something like and I put this here. Now, depending on what kind of study you're doing, certain temperature scales are used as opposed to others. In a science lab, you might use Kelvin. Well, this is going to be really cold if this isn't Kelvin, but it might also be Celsius. Someone might use Celsius, or they could use Fahrenheit. And so depending on Celsius and Fahrenheit, that could be significant. So you just want to be careful. Is this 32 degrees Celsius or 32 degrees Fahrenheit? That is a significant difference. So make sure you have your units attached to your numbers when you're working with quantitative. So anyway, there's something to keep in mind. Same if you were measuring, say, centimeters or inches. 1 centimeter is a sort of a distance like this. An inch is maybe something kind of, oh, it's kind of a big inch. Now, maybe something roughly like that's an inch, something roughly like that's a centimeter. Those are significant differences there. So you want to be careful that you make sure you have your units included. All right. So two other sort of comparisons that we make with data. And this might be a little confusing, especially when we talk about decimal numbers. Discrete versus continuous. So first off, discrete. So discrete data is countable. These are countable numeric outcomes. So you could be doing, say, a study where you count the number of, I don't know, golden eagles that fly past a bird reserve. And they're kind of rare birds. And you might count maybe 0, 1, 2, 3. Technically, you could keep counting, but most likely maybe 0 to 5. But you can count them on your fingers. Now, the thing about discrete data, it does not mean finite. You could go 1, 0, 1, 2, 3, on and on and on. Like if you were counting bacteria, goodness, you could be counting forever. So discrete just means you can count, the outcome is, well, you can count the different outcomes is what it means. And what I mean by counting outcomes, you could be doing this. There's 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.10, 1.0, 1.1, 1.2. Those are also discrete. You can count as you go. So if you can just count something, whether it's tick marks on a ruler, which still might be fractions of a whole unit. Like these are fractions of a whole unit. This is a tenths, 2 tenths, 3 tenths. Or you could be working with whole numbers, 0, 1, 2, 3. Those are all discrete. Digital thermometers, and this is the example they give in the text. You can have this digital thermometer that you say put it in your mouth. It gives this little reading. And let's say it goes, it's, you know, the discrete doesn't mean it isn't kind of a fine measurement. Fine is, and there's a lot of little measurements in between the whole numbers. But 98.6. Pardon my drawing. Give me some little artistic license on this digital oral thermometer. So 98.6, 98.7, 98.8. You'll get these sort of outputs, these stepwise outputs. So that's the example they give in the text for discrete data. The other kind is continuous. Continuous will be data that doesn't come in little steps. You can't say, well, this is first, second, third. You can't sort of label the different steps, different possible outputs. So continuous is where you just sort of measure until you stop. And the number you get, who knows what it could be. It could be something that's like 1.1. Measure again, you get 1.178940211. I mean, it's all kinds of numbers can come out of this. Any number you could actually think of. Well, as long as it's within the range of your, the data that you're looking at, the object that you're looking at. So continuous. This will be any possible real number. And where these continuous numbers come from, again, measuring lengths. When we're working with the digital thermometer, we're dealing really in tenths, like 98.6, 98.7, 98.8. When we're counting golden eagles, there could be 0, there could be 1, there could be 2, there could be 3. When we're measuring length, we could have 2 inches and then, again, 2.7892911184. So, any kind of real number is possible. And so the example they would give would be the old mercury thermometers. So typically we think of length is a good example. And with the mercury thermometers, this little mercury well, and then you have the thermometer. Put this under your tongue. And then you have some numbers here. Let's say there's 98.6. And what you do is you'll measure the length of the mercury. Now, in all actuality, on a mercury thermometer, you're going to kind of round off. If it's a little above 98.6, you might round it to 98.6. So you might turn this into a discrete measurement. But ultimately, it would be 98.64957. It could be some number. It could even be an irrational number. Excuse me. So, excuse me. Now, that's another thing to sort of talk about is countable numbers. If you're a little bit into number theory, this is really mathy stuff here. With number theory, countable numbers are like 0, 1, 2, 3, 4, 5, and so on. Negative, like -1, -2, -3, -4. Fractions, oddly enough, those are considered countable as well. In other words, you can come up with some kind of algorithm where you can, in theory, count every single fraction and you would never miss one unless you stopped. But if you follow this algorithm long enough, you'll eventually reach any fraction you're interested in. So that's what we might talk about countable numbers. Numbers that are not countable, these involve irrational numbers. These are numbers you can't represent as fractions. Think of a number that has just sort of a seemingly random distribution, maybe it is random, of digits behind it. Think of like pi or something like that. You can't represent pi as a fraction. So that would be a non-rational number, what we call irrational numbers. And so the set of countable numbers, that would be like your whole numbers, your net integers, negative integers, fractions. Well, like we label it countable. The set of irrational numbers are considered non-countable. It turns out there are so many irrational numbers, or the way irrational numbers are, the nature of their existence. You could not come up with an algorithm that would eventually get to one that you were interested in without skipping infinitely many along the way. So you can't come up with that algorithm the way you could for all possible fractions. So anyway, there we go. And kind of a mathy thing there, but basically you can think of it like this. If you're dealing with countable measurements, you're going to know what measurements are possible in one way. They're going to be some kind of a stepwise collection of measurements. It could be 1, 2, 3, 4, 5, 0.1, 0.2, 0.3, 0.4, 0.5, where you have these continuous measurements. You're just going to go out there and see what you get. And that's going to be what you get from continuous measurements. Discrete measurements, okay, you're going to find out what we're going to get, but we're going to have some idea of the sets of numbers that we could get as a result. If we're counting golden eagles, it's going to be a 0, a 1, a 2, a 3, or a 5, or a 6, or something like that. But if we're measuring a length that someone just showed up with, We don't know. It could be 2.0. It could be, again, 2.741897762. We'll have to find out. So it's one way of thinking between discrete and continuous. All right. So the book mentions some terminology. When we talk about discrete data, we often compare values using fewer we might say there were fewer golden eagles observed today than there were yesterday. For continuous data, we often compare values using less. So we might say the length of this stick is less than the length of this other stick. Again, sticking with length for continuous data. All right. So just a little note. Well, now we're going to get into something called data levels. Now, data levels, it's a way of looking at, again, types of data. So we've talked about quantitative versus categorical. We've talked about discrete, where it's stepwise, and we generally know what the steps could be, versus continuous, where we just got to measure it, and we'll see what kind of number we get. And it could be a small number, or it could be a number with a bunch of decimals behind it. And then before all of that, we actually talked about numbers we wish we had, like a population parameter, and then numbers we can probably get, like a statistical value. Now, when we talk about levels of measurement, we're talking about another way of looking at our data. We're going to have still quantitative and categorical to an extent. We're going to have, there's going to be some data that will be continuous. We have that comparison with discrete. This breaks it down a little more. So let's take a look at these. What's important about levels is this. Depending on the data you're collecting, it's going to determine what kind of computations you can do. So different levels allow possibly different computations. Actually, one level we're going to look at, categorical, isn't going to allow any computations at all. And we've already seen categorical. But we're going to take categorical and quantitative, and it's going to get a little more detail. So levels, it's sort of an interesting phrase, but bear with me. Let me show you how this breaks down. So the first level is what we call nominal. So this typically is going to be categories. So they could be, again, coded with numbers. So for example, we could say red is 0, green is 1, and blue is 2. And for whatever reasons, we decided to do this. Now, it doesn't mean if we took the averages of our recordings, that's going to be meaningful. And the range might not be meaningful either. So just because it's coded doesn't mean it has numerical value. In all actuality, it's almost certain not to have any computational significance. All right, and so we've talked about this before. Now, the order of these numbers might not have any meaning. Like, is there a reason red is 0, green is 1, blue is 2? I mean, why not just call blue 0, green 2, and red 1? As far as I know, that's perfectly fine. The order might not have any value at all, but sometimes the order of data does matter. So we get what are called ordinal data. So nominal, you can think like categories, like Democrat, Republican. You could say in-state, out-of-state. You could say, again, red, green, and blue. Now, ordinal data it can be put in order. You can put the data in some kind of order. So for example, letter grades. So we've seen these before, A, B, C, D, and F. So you can put these kinds of things in order. So let's say we have a quiz in class and everyone takes their quiz. You get a letter grade at the end. Let's say it's a 10-question quiz. You would have an A, B, C, or D, or F on the quiz. Now, the thing about this, though, is that differences might not be valuable here, or they're difficult to find. I need to be careful here. I want to make sure I explain what differences I mean, because we can mean different as something just simply not being the same. What I mean by differences, subtraction in this case. If you try to subtract the data values, it might not mean anything. Like, what's A subtract C? Now we know A and C are different grades, and A is a higher grade than C. That makes this ordinal data. But what is the result if you subtract C, a letter grade of C from a letter grade of A, if the only thing we know about the grades is A and C. Now, what we would want, excuse me, if we had the number of points earned for the A and the points earned for the C, then subtracting the points earned could make sense. But we could figure out, for example, how many more points did the student who had an A earn than the student who got a C. But if we just have the letter grades to work with, we don't know. So A minus C is going to be meaningless. All right. Now, again, this kind of data it's not fit usually for calculations. So usually not fit for calculations, just like nominal data. All right, so we have nominal data, categories. There's no rhyme or reason with order or anything like that. Ordinal data could be in somewhat ways categorical, but there's an order to the categories. All right, so let's take a look at the next one, interval. So here, this is data that you can arrange in order. Differences and again, they use this word differences in the text. What they mean is subtraction, not just that the data, one datum is different from the other. And they're meaningful. So examples they give, calendar years. How many years has it been since the year 1900? Well, you take 2021, subtract 1900. So there's a difference there you can compute. The other one is temperature. If my temperature is 98.6 degrees and I use a thermometer and find my temperature is 100 degrees, I can calculate the difference of temperatures. Now, there's something interesting about this, though, and it's going to be important when we get to the next and last category, and it's this. The choice of zero in our measurements is arbitrary. Or this is kind of, I'm going to use what they say is not a natural choice. And I'm going to put natural in quotes. This could get kind of confusing. The idea, really the term arbitrary might be a better way of putting it. What I might say is subjective. And let me give you an example of why. When they talk about natural, I think they mean in the sense of science. And this becomes particularly, well, a good example of this might be temperature. Let me explain. So if we take a look at temperature, we have 0 degrees Celsius. So that's the 0 we've chosen if we're using Celsius. But this is 32 degrees Fahrenheit. The 0 degrees for Fahrenheit is somewhere down here. So what that means is that the temperature that we feel, the temperature, it's the number, if I recall this correctly, it has to do with the vibration of molecules. If they're sort of have energy in them, they tend to vibrate. So the vibration, the energy available to make the molecules vibrate and bounce off of you, it's going to be the same, but we label the condition, the same condition, 2 different ways. If we think in terms of Celsius, we label this condition 0 degrees Celsius. That very same condition, the energy, the molecules, all of it's still the same. We could also label it 32. So which one's right? Well, we don't worry about that. We decide if we want to use Celsius, then the state we're in, if it's the state where water freezes, we're going to call it 0 Celsius. But if we're using Fahrenheit, we're at that point where water freezes, we're going to call it 32. So the idea of interval data is that the starting point, the 0 point of your measurement, you kind of choose it subjectively. And there's reasons for using different starting points for 0. Natural, again, I think in terms of science, where we might talk about absolute 0, we talk about kelvins, that might be a quote-unquote natural 0. But the point really here, when we're talking about interval data, is you get to decide really where 0 starts. Or someone decided that if you're using someone else's measuring system. But the placement of 0 could be subjective. And there's different reasons for using 0 at different points. Just because it's not quote-unquote natural doesn't mean it's not going to get the job done. So you don't have to do everything in Kelvin, in other words. We always use Fahrenheit. So, and that works for us perfectly fine. Anyway, the last category is ratio. So the data is arrangeable in order. Differences or subtraction is meaningful. And also, so this is what we had for interval data. Also, again, they use this word natural. There is a natural 0 or natural starting point. One other thing. Ratios of data are also meaningful. Now you might be thinking, why couldn't I take the ratio of temperatures? Things like that. We'll talk about that. Like, let's say it's 40 degrees. compared to 20 degrees. So the temperature is twice as much as it was before. Isn't that a ratio? Well, hold on, I'll show you what's going on here. So examples of ratio data are height and, say, class time. So when they talk about natural zeros, there's really an idea of zero with height that we typically can agree on if we're measuring the heights of things. Now, you can argue this point. You might argue that, well, what if we want to ignore the first, say, I don't know, the beginnings of like trees or something. We're interested in only the top parts of trees. Then I might, okay, fine. And that seems like you're challenging the idea of a quote unquote natural zero. But if we're talking about the heights of trees from the ground up, not counting the root systems, I guess we do have to state that, you would have essentially a natural zero if we all agree upon the ground as the starting point. So that does kind of sound like agreeing that the freezing point of water is just going to be zero. So, but if we're talking about the height of people, when we talk about the height of people, as far as I know, there's no convention where you would ignore the beginnings of, say, the bottom part of the foot or something like that. And so in that sense, we would have a natural zero. We measure the height of the entire vertical person. Class time, how much time is in a class? If we say we want to know how much time is in the class or when class starts officially to when it ends officially, well, you could have a class that's zero. Maybe it got canceled. So we might have a natural zero occurring there. Now, one of the things that could be confusing here, and again, you kind of saw this, if we're talking about, say, the heights of trees, you know, we did seem to agree upon a convention, like we would agree upon 0 degrees Celsius as being the temperature that water freezes at. With the trees, we make sure not to count the root systems in the height. We might say, you know, it has to be from the ground up, not above some part of the trunk, and then we measure the height. For example, if you're looking at like pine trees, you know, or many trees actually, oak trees, pine trees, you have the trunk and it's bare, there aren't branches coming out of it, and then you get the first branch. And then maybe you want to measure the height from the first branch up or something. That might be another way of defining height, depending on what you're interested in. Anyway, well, how do we really determine between interval and ratio? And there's a couple ways they do this, or a couple ways they recommend this. So one is called the ratio test. And again, this could be a little tricky. So let me go through the example of temperature. And again, it has to do with something else. And let me give you the other standard. The other test is this. It's called the true zero test. Is there a natural zero? Again, we've mentioned this before. So let me talk about temperature. Why would we say 40 degrees versus 20 degrees? Let's say we're talking Celsius, that actually fails the ratio test. That even though 40 is twice 20, if you take the ratio of 40 over 20, you get 2, but that fails. How? Well, it has to do with the location of 0 degrees Celsius. What 40 degrees means is 40 degrees above 0 degrees Celsius. 20 degrees means you're 20 degrees above 0 degrees Celsius. Now, you can have negative values of Celsius. So here comes the problem. It would be very tempting to say that we're going to compare 40 degrees Celsius versus 20 degrees Celsius and argue that this passes the ratio test. Here's the thing. Here's 0 degrees Celsius. And again, we've talked about this not being a natural zero. I'll explain why. It's 40 degrees Celsius. Here's 20 degrees Celsius. I mentioned earlier something called Kelvin. Kelvin is a type of temperature measurement. And Kelvin has something called absolute zero. The idea is this. What if all warmth, all phenomena that could cause a temperature to exist was just gone? Let's call that absolute zero. Again, we're thinking of temperature, and okay, I'm not a physicist, so I'm sure this is probably more complicated than I'm making it out to be. But let's say we talk about the vibration of molecules. Well, let's say we have a state where none of the molecules are vibrating. The energy is just not in them anymore. They're just still. Nothing's moving, solidly still. Well, because even solids, like us, we actually have molecules in us that are vibrating. That's why we're warm. Let's say, though, you can get things so cold that the molecules don't vibrate at all. Again, solid objects have vibrating molecules. Let's say even those aren't vibrating. We call this absolute zero, or 0 Kelvin. So what is 0 Kelvin in Celsius? Well, or let's compare our Celsius measurements rather. 40 degrees Celsius in Kelvin is 313.15 Kelvin. 20 degrees Celsius in Kelvin, 293. Put 0 Kelvin over here. I know it says it looks like OK, it's really 0 K. Let me see, I don't remember what the number is for 0 Kelvin. Pull that up real quick, pardon me for just a moment. Let's take a look. Minus 273 degrees Celsius. That's what 0 Kelvin turns out to be. So when we're talking about temperature, and let me just do one quick conversion, make sure my conversion's here. Do the wrong numbers here, that looks good. Okay, good. So here's the thing. 0 degrees Celsius is not really the zero temperature of the cosmos. The idea is that when we measure temperature, we're in a sense measuring the presence of energy. And even though we use our 0 degrees Celsius, we get a 40 degree and a 20 degree. Really, the total amount of energy, or the presence of energy, is really going to be using these bars, or these here, that go all the way down to the natural absence of energy, the natural zero. And clearly this bar is not twice as big as this bar. So the reason we're careful when we talk about ratio versus interval is that we could choose a zero that might make it look like there's a ratio of 2 to 1, 40 divided by 20 is 2. But if we look for a natural zero, when the presence of energy is just gone, again, I'm not a physicist, I hope I'm not butchering this, but let's say that's what we're looking for. Based on that natural absence of energy, this is not twice as that. This is not twice as that. And so that's why that quote unquote natural zero is necessary in some ways to determine if we have a ratio or not. And if we are using a so-called natural zero, we can't go anywhere below this, that's it, then we can start talking about ratios of data we've collected. So that's the issue with the ratio test. When you can choose your zero to maybe here, and there could be good reasons for that. Again, if we're talking about something where we can't have water freeze on us, it just can't happen, then we might choose 0 to be where water freezes, because anything below that, it's not going to do us any good. So there could be very good reasons for choosing a subjective 0, but you want to be careful. So an example is something that you would pass a ratio. Let's say we have heights. And let's say we're talking about the ground. So height above ground, we select the ground to be our 0. And then we have 100 feet for measurement 1, measurement 2 is 50 feet. Then what we have here is a natural 0. We're saying heights above ground, and we choose ground to be 0, and this is, say, a level surface. Then we could talk about 100 over 50 being 2 to 1, something like this. We can talk about ratios. All right. Anyway. So the next topic, so we talk about data types. You've probably heard this before. It's called big data. And big data, they mention in the book, and I better mention it here, the definitions vary. But this is the definition of the text. It's a collection of data that's so large. And you think about population data, it's like, golly, could you actually gather population data at some point? Well, possibly. It's a data collection so large that its analysis is beyond the capability of traditional software. Now, to be honest, I'm not totally sure where they're drawing the line here. What you can do, and I'll mention this, I'll introduce you to a statistical package called R. It's free, it runs on your computer, it's pretty cool. You can calculate means, standard deviations, correlation coefficients. It's a neat tool. But there are data sets so large that if I tried to do any computations with them on my little computer using R, it couldn't do it. It would just take too long, or I don't know, maybe it would crash. The text says that these kinds of data sets, you're probably familiar with bytes, like you measure movies and stuff, little video clips, maybe 9-10 minute video clips, and say gigabytes, maybe 4 gigabytes, depending on the resolution of the video. These are measured in terabytes, which is 10 to the 12 bytes. And I'm sure it doesn't stop here, but we can go up to yottabytes. Now let me look something up real quick here, since it did come up. Let's see what gigabytes is a power of 10. It's a billion bytes. So for reference, 1 gigabyte is 10 to the 9 bytes. Now we do have hard drives that are now terabytes, so in a way we're sort of getting to a point where, at least by the textbook standards, we can handle some of the lower end of big data. So some examples of big data. So GPS data, from smartphones. I'm not sure exactly how the apps work, but if you're using, say, like Google Maps or something, you might say, okay, Google, tell me how to get from where I am to Trader Joe's. And it'll locate you and then locate Trader Joe's and hopefully find an accurate route. And there's all this GPS data. This is not only generated from people all around the world every day, but it could be generated many, many times throughout the day from, who knows, maybe even like 1 billion people. So this is happening many times every day from, and maybe 1 billion people or more. That data set's going to explode, at least in size. Another example . So if there's a flu epidemic coming, if you could see people searching, well, what are flu symptoms? And maybe it's been a while since they had the flu. Remember, they've never had the flu. Maybe they're having the flu in sort of like a different sort of type of physical health. They might have just had surgery. Maybe they're exercising. You see people searching for flu symptoms. Well, it could be just random, or there could be a flu starting out. People are getting sick, friends are getting sick. So you might ask the question, well, how often are people searching for flu symptoms? That might be a clue that, well, there's some flu spreading in the community. And again, it depends how many people are searching, how often they're searching. That might give you an idea, and that could be a really big data set. So big data could be stuff like this. Lots of people contributing lots of data all the time, multiple times. The data sets could get massive. So the computational devices, say typical desktop computers or laptops or smartphones, they might not have the processing power to do all these computations. So we might need special tools and software that can manage those tools in order to make these calculations. So let's see. This takes us to data science. And so here what we're going to do, in data science, we're going to apply, well, the subject of statistics, which you're learning about now. We're going to apply computer science. Software engineering. And then other fields. And some of the other fields they mention fields, for example, like sociology. You know, what kind of data is going to be meaningful for what we're trying to understand? So statistics, what you're taking right now, the textbook mentions, if you want to get into data science, you're already on the right track. You're headed in the right direction by taking this course. Computer science, we might be interested in parallel processing. If we have all this data to analyze, we might want to try to do some parallel or simultaneous computations with this data because we got to go through all of it. Handling one piece of data one at a time might be that might be too time consuming. Software engineering, maybe you're going to do some programming. And this is where R really comes in. R is, you can think of it as a programming language as well. And you can write some little programs to take in data from a spreadsheet, maybe look for any missing data values. We'll talk about those in a bit. And then with the data that you keep, do some kind of calculation using the built-in functions in R. And then again, other fields. Do you have the expertise in a field to recognize what is it that you want to make computations or analyses of? All right. Now, with data, and especially big data, you have to worry about this. You have to worry about missing data. So there's a lot of different reasons you could be missing data. And if you're working with large data sets, you'll try to come up with algorithms, little programs that will look for these missing data values, and well, there'll be some procedure you'll write out in your program on how to handle them. So missing data, it's not uncommon. So for example, in surveys, the responses might not be recorded, or were lost. The responses may have not been recorded, or they were lost. So let's say someone's collecting some survey data, they're walking around campus asking questions, and let's say they have 6 pages of yes or no, do you support this new park they're going to build in this particular location in town? And you ask everybody, do you support it, yes or no? Or are you for this, yes or no? And as you're walking the class, page 3 slips out. The wind catches it. You don't know it slipped out. And it blows away down the hall, out the door, and it's gone forever. And so you get to class and you present your data. You have page 1, 2, 4, 5, and 6. Page 3 is gone. So you could lose the data that way. Now, you want to be careful here, and we've talked about this before with surveys. Responses might not be recorded because, well, the subject didn't want to respond. Again, you could be talking about something that's, well, maybe kind of controversial, and people might not feel comfortable saying they support something and they don't support something. They might not feel comfortable about that. So they might say, well, they'll give you some information, and then that one critical response, I don't want to say. So what do? What we realized last time is that the non-response might be very significant. There might be a point of view that we're interested in learning about that, well, it's hidden in all these non-responses. And if we ignore those, well, that means we're going to ignore that point of view. It doesn't get to be part of our study. And if we publish our study, well, if that point of view doesn't show up and we're going to try to represent everybody in our community, this group of people won't be represented. We're going to have a biased study, and any conclusions we make could be misleading. So we want to take non-response seriously. So ignoring missing data can create misleading results. Now, this isn't always the case. There are circumstances where if we're missing data, we might be able to ignore it. And let me give you at least a general idea of what that is. Missing completely at random. what this means is that there's no systematic or consequential reason why the data values are missing. In other words, the likelihood a data value is missing is independent of that value. So the likelihood a data value is missing is independent of that value. So let's think about the park situation. Let's say someone wants to put in this really neat park, and it's going to have like a pool, there's going to be a pond with ducks and geese, there's going to be all kinds of just activities, devices, exercise machines, maybe a playground for kids, these kinds of things. People are going to really enjoy this park. And you go around, hey, do you support the creation of this park? And everyone you seem to interview says yes. And very, very few people say no, but you have a whole bunch of non-response. And it could be a lot of people aren't responding because the location of this park is maybe in a location that's going to cause a lot of congestion, a lot of traffic in the surrounding streets, like it's near busy boulevards, and maybe it's not a safe place to put a park, especially if kids are running in the roads. And then the people living next to the park, if this park really is incredibly popular, it's going to get pretty loud. So some of those non-responses, the no, well, there's significance behind that no. Now, they don't want to be the kind of person that says no to all this fun in park. Maybe that's something they're concerned about. So they don't say anything, but maybe they don't really want it. Now that would be a connection between the data value, no, and the response not being there, if that situation turned out that way. But there are situations where it doesn't matter. Let's say you're missing data because, well, let's say you do this very randomly. You do a random sample of people from Roswell, and you record the results on your random sample on 6 sheets of paper, yes, no, and you lose page 3. Well, if it's a random sample, then there's no bias in the pages, like page 1 tends to be yes and page 4 tends to be no. We're not going to have that kind of a bias. It's going to be random. The responses will be randomly distributed, or, well, the people will be randomly distributed throughout the study, and hopefully losing page 4 doesn't lead to some bias. Oh, maybe it does. But the idea is this. The absence of the value has nothing to do with the actual value itself. It just so happened that for this subject and this value, someone forgot to record it. The example they give in the text is if someone is, for example, entering data and they hear their favorite song and they accidentally skip over the last data value. They don't put it in, or they put in this totally wrong number that we can all see is wrong. Well, then that has nothing to do with the value that was supposed to go in there. So we think, you never know, but let's say it really didn't. Well, then that would be that the likelihood a data value is missing has nothing to do with the actual value of that data or that datum. So when that's the case, we might be able to ignore that data or that data value. We might be able to replace it with something. We'll talk about that in a little bit. So as long as the actual value has no effect on whether it was included or not, then we are missing completely at random. And that's something we can do a little something about. There's something we can do about that. If the value of the data value had nothing to do with why it was excluded, all right, we fall into this. Now, the other situation, and then they summarize it. Another way of putting this, all data values are equally likely to be missing. If the no response is missing, there's an equal likelihood that a yes response could be missing. So that's right. So when they're missing because it's completely at random. All right. Now, what we've seen before, though, was not this case. And this is called missing not at random. And here, the value, let's see how they were. The value of the data is related to the reason it is missing. Again, this could be a person who, if you ask them about this controversial park, they might say, oh, I don't want to answer that. And there could be different reasons for why. It doesn't have to mean that they are against the park. They could be a person that's for the park. They really think it's a good idea. They don't think the traffic is going to be bad. They're going to be fences that keep kids from running in the street. And the park has hours, and it's a huge park. There's going to be huge grass fields around all the areas where people are going to really concentrate. So there'll be some reasonable distance and some trees to buffer sound. So they've looked at the details of the park. They think it's great. So they want to say yes, but all their neighbors are vocally against it. And so they don't want to say yes. So in that sense, or it's you don't want to say no because all your neighbors are for it, but you don't want them to know that you said no. Well, again, that means the value of the data, that's why they didn't want to respond. And this is where we do have a problem. Well, we have a problem with the other one too. We'll talk about that more. But here, we got to worry about bias, issues like that. So let's see. So again, an example might be in a survey. Giving a non-response to a controversial question. So again, the non-response could be very significant. All right. So what can we do about this? Well, if values are missing completely at random, if values are missing completely at random, what we could do, we could ignore those subjects with little bias entering in our study. So if the reason these values are excluded had nothing to do with the actual value itself, if one value is equally likely to be excluded as, say, any other value, then what we could do is take subjects, people we've interviewed, and just leave them out of the study. We'll say, we didn't get the response. We'll remove this person, that person, and just remove the persons whom we don't have values for. Again, this could be someone who's doing the data entry, and to keep bias out of it, we might not tell them what the different values of data mean. So they don't know what the people are responding to, or they're just a yes, no, no, yes, no, or maybe we code it. And we say yes is 53 and no is 48. We don't tell them that's what those numbers mean. We just say, here's a bunch of 53s and 48s in this spreadsheet. We need you to transfer them over to this or something like that, or maybe, or who knows. And so the numbers don't mean anything to them, and they're just listening to their favorite song, and they accidentally mess up some values here, then values here, then values here in the spreadsheet. They're not picking or choosing for any particular reason, as far as we can tell. Well, then where they made their mistakes, hopefully it's not too many, we can leave those subjects out. Now, there is a consequence, though. There is something we want to be careful. Is that, well, we'll get to that in a bit. So if the values are missing completely at random, we could ignore those subjects. So I'll mention this. One of the problems is that this could reduce, actually it will reduce, it's going to reduce your sample size. Remember, when we come up with a sample is supposed to reflect the population. So when we're pulling subjects out, we're going to reduce the sample size, and well, we better hope that the sample that's left, even though there might not be bias regarding how the values were left out, we also might want to check the integrity of our sample, especially if we're dealing with a relatively small sample size. If we're interviewing 1,000 people and we have to remove 5 subjects, okay, we might be all right. If we have 15 people and we remove 5 subjects, that could change things radically. So I want to be careful. I'll put this in quotes. You might need to take a look at your sample, check the integrity of your random sample to make sure that this is the case. So again, got 1,000 people, 10,000 people. If you have to remove 5, it might be okay. But if you've got 15 people, you remove 5, that could be very significant. So again, this could come back to haunt us. So now, if we have this, another solution we could do, if we have this situation, the data is missing for completely random reasons, we can input missing data values in a nutshell. We're going to make them up. Now hold on, let me explain. We're not going to be crazy with this. This is a little bit, I don't want you to get the idea that you can just put in anything you want. You can't do that. So when we make them up, I'm going to put a big arrow on this. We're going to make them up appropriately. In other words, if you're doing this survey about yeses and nos for the park and you have missing data values, it doesn't mean you get to plug in yes because you get to make them up. You have to do this appropriately, ethically, responsibly. An example of this, a technique that where it's appropriate, what people have used in the past, go replace values with means. Or averages. So you can replace that's been done before when it was appropriate. One that sort of I think I tend to be drawn to would be something like this. Random values from previous study. Random values from a previous study. And I'm really, and I should say related. Or similar. I think the book uses similar. From a previous similar study. So let's say someone studied this before, maybe they had a slightly different sample size, but not drastically so. You're trying to, well, in a sense, do the study again for whatever reasons, and you've got some missing values. If it seems appropriate, like you could use random values from their study to fill in for the ones that you're missing. So again, it seems like you're just making them up because you didn't measure. You're not putting measurements that you made in there, but appropriately, ethically, responsibly, you're going to replace those values. And techniques used in the past, people sometimes replace them with the means of data, data means averages, when it was appropriate. Or they would use data that's randomly chosen from previous similar studies. So those are just two examples. There are other things you can do. All right. Now, when data is missing completely at random, again, the reason one value is excluded from another, there's no reason for that. It's all random. You're much as likely to have a yes missed as you would a no missed. When you're in that situation, one of the options was just to remove those subjects, basically just ignore them. But double star this. Ignoring data values missing not at random can introduce bias. Ignoring data values missing not at random. In other words, there's people tended to not want to give this kind of a response. Removing those, pretending those don't exist. And again, we've covered this before. That could introduce bias into your study. So that's something you do want to, if you think there is a reason why data values are not showing up, that's going to be a problem. So we'll have to look at that at some point in the future. So one of the things you're going to want to always do when you're doing statistics, determine why values are missing. it going to be randomly? Not randomly? Does this hurt your sample? Does removing them removing those subjects hurt your sample? And particularly, does sample still represent your population? Accurately. So if the values are missing at random, there's equal likelihood for one response to be missing as it is for another response. Well, then we could probably ignore those. We can, all right, we'll ignore them. If there's not too many of them, if there's too many, it might make our sample too small, or it might do something else to our sample where we might not have a sample that accurately represents our population. One of the things I remember in my statistics homework assignments when we would take some data and do data analysis is that we would need to try to explain missing data. Did it look like data was not input correctly? Or there was a value that was put that doesn't make any sense? Like if you're computing, say, temperatures in the city of Roswell at noon, and for some reason our temperature is recorded in July of 1 million degrees Fahrenheit, then that's not going to be possible. And if I was in Roswell at noon and I'm still not scorched, then that probably was an accident. Maybe they meant 100 degrees Fahrenheit instead of 1 million. They accidentally, they're recording it, let their fingers sit on the 0 key a little too long. So you would take a look at those data values and try to understand what went wrong and then decide what you want to do with them. Were you going to exclude those subjects? Would you maybe use an average of data values, maybe use, again, data values from a previous and similar study? You have to take a look at what your options are. What's the appropriate response? So there you go. That's section 1.2. If you have any questions, let me know.